Now, we've already talked about software implementations of ADCs in our MSP430 environment. Now we'll talk about hardware implementation. So a chip, in this case we're using the MAX1111, and that chip will allow us to interface with it and do all the conversion and things inside it. We just need to communicate with it somehow. So there's several reasons we might do something like this. Sometimes we might have a microprocessor or a microcontroller for that matter that doesn't actually have an ADC. And so in that case we need to use an external ADC like that MAX1111. Sometimes that ADC internally might not be fast enough. It might be a slower ADC, or maybe we need more bits of resolution, or we need more things that we're actually measuring. So we could use one or more than one external ADC to perform this. In terms of looking at the features of the MAX1111, we've got an 8-bit conversion that we're performing. So 256 different voltage levels that we can encode. Successive approximation converter, so it's that binary search style one. It's 8 channels, so we can have 8 inputs into it. SPI, serial peripheral interface, that we're interfacing with it. And our maximum conversion time, which because it's successive approximation converter is our standard conversion time, is 20 microseconds. So reasonably fast conversions that are happening here. Here's the architecture of our MAX1111. And we'll be talking about some of these different elements and how they actually work. So firstly, our input multiplexer, or our input mux. We've got 8 different channels that we can multiplex in to a hold circuit. So we can't measure all of those 8 channels simultaneously. We can only measure one at a time. And so our multiplexer will select the one that we want, we tell it which one we want, and put that voltage, and switch it through to a hold circuit. When we've got in our hold circuit, it will create that voltage inside, and that's the one we're actually going to measure. So we can select as a user which channel that we want for sampling at any point in time. We can keep changing them as we go. We then have a reference voltage. So in this case, a 2.048 volt reference voltage is internally generated. Now we can connect this to our reference pin and use this as the reference voltage. Conversely, we might want a different reference voltage. We might want to use 3.3 volts or something like that. We can feed that in, but we'll need to make sure that if we want accurate conversions, that reference voltage needs to be stable. We can't have a voltage that's kind of moving around, drifting around, because that won't give us a very good conversion. It won't be a stable voltage that we're doing our conversions with. We've then got what we call track and hold circuitry. Basically what we want to do is when we're not performing the conversion, remember the conversion takes a finite amount of time, we're not always going to be converting. We want to track the analog input, whatever is connected through using the mux. When we're actually performing the conversion, we don't want that analog voltage to be moving around. We want to hold it there while we're performing the conversion over that 20 microsecond period. So that's what the hold circuitry does there. So this is a bit what it looks like. We've got a number of different channels that can feed in there. We select whatever channel we've got using our multiplexer. We have a switch there that we can put in 2 modes. We've got the track mode, where if we put in the track mode, we create an RC circuit, and that RC circuit consisting of that capacitor, the whole capacitor, and our resistor, will track whatever input is on our input multiplexers at the start there. When we want to perform the conversion, we switch it over into the hold mode. When we've switched it over into the hold mode, we've disrupted that RC circuit, and that capacitor there will be holding whatever charge that we had there. That will feed into our comparator, and we actually perform our conversion at that point. Using this technique, we'll basically be holding our input voltage constant or near constant for the conversion period. Our next part's the successive approximation block. And that successive approximation block performs our binary search, successively 1 bit at a time, honing in, removing half the search space and working out what our analog voltage is. It uses our ref in as our voltage reference, or whatever reference is supplied to it, and puts the result in an output shift register, a series of bits that allow us to work out what our analog voltage output is. This is how we connect it up to our microcontroller or microprocessor or whatever we're connecting it up to. I've mentioned it's SPI. We've got our clock bit and our data bits, both in both directions, it's bidirectional, and a chip select bit as well from the microcontroller telling this device that we're actually using it at this point of time. One of the things about SPI is It's a bus configuration, so we can have multiple devices all connected to the same pins, each with a different chip select, which we use to choose each one. So this gives you the background knowledge now to actually configure something like this, connect our microcontroller up to our ADC, an external ADC, and get data off it. Now, I'm not going through all the code because we haven't actually covered SPI in detail yet. But essentially, we've got a series of commands that we use from our microcontroller. We send commands to this ADC and say, perform conversion on this particular pin, and it will give us back our data.